Okay, in this class I'm going to look at revisiting working power, this time with some slightly awkward angles. I'm just going to move some of this information up out of the way because space will probably be an issue here solving this problem. So it says complete the force diagram and find any acceleration. Again, I'm just not making these questions too wordy because of space, but hopefully at this stage you're able to draw force diagrams yourself to a certain extent. I've got clearly a particle on a horizontal ground, and it has a weight here of 50 g. There's some kind of tractive force maybe, or tension maybe pulling it up here in this direction, I should say. So we'll assume this is a string here, and there's a tension in the string of 150 newtons. Remember, the pulling force on an object by a string is called tension. That's the name of that force. We'll also have, because it's sitting on the ground, there will be a force on that object by the ground, and that force is called a normal reaction. Or, watch out, or is not going to equal to this downward force because there's a lifting force here as part of the pulling on the string. Also, we're told that the coefficient of friction is 1/4, so there'll be some kind of friction force acting. So there's my force diagram. That's it. That's a force diagram. Now I'm going to find any acceleration. Well, there'll be no acceleration vertically. One thing I'm going to do, is I'm going to think about just resolving this tension vector into its horizontal and vertical components. It tells me tan of A is 3/4. Well, that's suggesting a special triangle. Tan of A is 3/4. Right triangle, 3, 4. By Pythagoras, that's 5. We're talking the ratio of, remember that's opposite over adjacent. So opposite to adjacent to hypotenuse is in the ratio 3 is to 4 is to 5. So this 150, well, that's 5/30s. So the opposite is going to be 3/30s, has to be 90 newtons. The adjacent is going to be 4/30s, has to be 120 newtons. Okay, so there's a lifting force there of 90 newtons, which tells me, or has to be equal to, well, let me say it this way, or plus that 90, those my up forces, have to equal to my down force, which is 50 g. So or is going to be equal to 50 g, subtract 90. My friction force, well, again, I have to think about my maximum friction. The maximum value friction can be, what is it? I'll just narrow my pen a little bit for space saving purposes. Well, the maximum friction force we can apply is going to be 1/4 times 50 g minus 90 g. So that's going to be 25 g over 2 minus 45 over 2. Minus 45. So again, take g to be about 10, that'll be 250 minus 45, 205 divided by 2. It's about 102.5, which is going to be less than that. So that means there is going to be some acceleration. So friction is going to use all of its possible magnitude here. 25 g minus 45 over 2. Okay. In fact, I might just tidy that up a bit. 25 g, just 25 times 9.8. I'm going to subtract 45 and divide by 2. That actually works out to be about 100 newtons. Okay, so I'm going to use that. I'm going to use that 100 newtons there of force of friction acting back. So I want to find any acceleration. Well, any acceleration is going to be found using the equation F net equals ma. The net force here is going to be 120, subtract that 100, well, that's going to be 20 newtons, and that's going to equal to the mass of the object. Well, if its weight is 50 g, its mass has to be 50, and that's times a. Okay, so the acceleration we can work out there is going to be 20 over 50, which is 0.4 meters per second squared. Okay, so that's the acceleration. Find the work done in moving the block over a horizontal distance of 2 meters. Well, there's different things doing different work. If we look at the work done by the string, well, we know that work done is equal to the force applied in the x sense multiplied by the displacement in that sense. The force multiplied by here is 120, and it's been moved, what did we say, 2 meters, so it's 20 times 2, which is going to be 240 joules of work done. So there's 240 joules of work done on that block by that string. Okay. Friction is also doing some work, but that work will be negative because the force and the displacement will be in opposite directions. Okay, it'll be negative 100 times 2, negative 200 joules of work done on the block by friction. Okay, but generally when they're saying find the work done on the block, they're talking about, you know, the work done in moving it as opposed to work done in preventing it moving. Let me look at another question with maybe awkward angles. Here we have a force diagram for an object moving uphill with a constant speed. I'm told its power output is 440 kilonewtons. I want to find out how fast it is traveling. So how fast is it traveling? Well, power, you know, let's think about this for a second. Power is defined as work done over time taken, but work done is defined as force by displacement. So we've got force by displacement over time, which is force times the velocity. So the velocity can be calculated using the equation V is equal to P divided by F, the force. So the velocity of this object is going to be the power divided by. So a couple of things we're going to have to do is we're going to have to resolve this vertical force into its perpendicular and parallel components, perpendicular parallel to the plane. There's my angle. That's this angle in here. It's always the same as the angle of inclination. Remember, this is going to be 100 cosine the angle. This one is going to be 100,000. It should be 100,000, of course, times cosine of the angle. It's 100 kilonewtons. So it's 100,000 times the cosine of the angle. And this one in here is going to be 100,000 times the sine of the angle. And we know from our information here the sine of the angle is 1 in 50. So essentially we're dividing by 50. Dividing by 10. We get rid of one of those and then we divide that by 5. I think that's going to work out as 2,000 newtons. Okay. One thing to note here is this thing. It's telling us that the object is traveling with constant speed. That means the forces in any direction, you know, opposite forces I should say, must be equal in magnitude. So if we look at this along parallel to the plane, that T force pulling it up, that tractive force driving it up along the hill, that has to equal to, well, that 20,000 force acting against that combined with this other 2,000 acting against it also. So the tractive force is going to equal to 22,000 newtons. Okay, so that's my tractive force. How do we find the velocity? How fast is it traveling? Well, we said constant velocity is the power over the force. The constant velocity here, the power output is given as 440,000 newtons, sorry, 440,000, that's kilowatts, not kilonewtons, kilowatts, divided by the force, well, that's the tractive force there, which is 22,000. So we're going to have 440 divided by 22 with a bit of cancellation. 22 goes into 40 twice. I think the velocity is going to be 20 meters per second in this case. Okay, so working power with awkward angles, slightly awkward angles, doesn't make them too much more complicated. Remember, power is work divided by time. Work is force by displacement. Displacement divided by time is average velocity. However, if it's traveling with constant velocity, its average velocity is the same as its instantaneous velocity. Here, the velocity is going to be the power output divided by the driving force, which is T. Okay? Okay, so practice questions. We're in 6A in our textbook. I'll be moving on to the next section in the next class on energy, 6B. If you have any questions on that section, give me a shout, let me know, contact me through Teams, please. Okay.